sklearn covarianceoas. Description: explain in detail. The sklearn covariance module provides tools for estimating the covariance matrix of a dataset. Covariance matrices are fundamental in statistical analysis, as they quantify the relationships between different features of a dataset. Inputs. Input 1. Explain in detail. The input to the sklearn covariance module is typically a dataset, represented as a NumPy array or a pandas data frame. Each row of the dataset corresponds to a data point, and each column represents a feature. Input 2. Explain in detail along with the dataset. You might also provide information about the type of covariance estimation you want to perform. This could include parameters like the regularization strength for robust covariance estimation or the number of components for dimensionality reduction. Outputs. Output 1. Explain in detail. The primary output of sklearn covariance is an estimated covariance matrix. This matrix is a square matrix, where each element represents the covariance between two features. The diagonal elements of the covariance matrix represent the variances of individual features. Output 2. Explain in detail. Depending on the specific covariance estimation method used, additional outputs may be provided. For example, methods like graphical lasso also return a precision matrix, which represents the inverse of the covariance matrix. Steps. Step 1. Explain in detail. The first step involves loading your dataset and preparing it for covariance estimation. This might involve scaling or standardizing the data, depending on the chosen method. Step 2. Explain in detail. The second step involves selecting a specific covariance estimation method from the sklearn covariance module. This could include methods like empirical covariance, Leduit-Wolf, graphical lasso, or shrinking lasso. Each method has its own strengths and weaknesses, and the choice depends on the characteristics of your data and the intended application. Metrics. Metric 1. Explain in detail. One metric used to evaluate the performance of covariance estimation methods is the log likelihood of the data under the estimated covariance model. Higher log likelihood values generally indicate a better fit. Metric 2. Explain in detail. The Frobenius norm of the difference between the estimated covariance matrix and the true covariance matrix is another metric used to assess the accuracy of covariance estimation. A smaller Frobenius norm implies a more accurate estimate. Visualization plots. Visualization plot 1. Explain in detail. The estimated covariance matrix can be visualized as a heat map, where the color intensity represents the magnitude of the covariance between features. This can help to identify strong correlations and dependencies within the data. Visualization plot 2. Explain in detail. For methods like graphical lasso, the precision matrix can be visualized as a graph, where nodes represent features and edges represent the strength of the dependencies between them. This type of visualization is useful for identifying conditional independence relationships between features. Fine-tune parameters. Parameter 1. Explain in detail. Many covariance estimation methods in sklearn covariance have tunable parameters. For example, Leduit-Wolf has a parameter called assume-centered that specifies whether to assume the data is centered or not. Parameter 2. Explain in detail. The graphical lasso method has parameters like alpha and tol that control the regularization strength and convergence tolerance, respectively. Uncertainty methods. Uncertainty method 1. Explain in detail. Some methods in sklearn covariance provide estimates of a uncertainty in the covariance matrix. For instance, Leduit-Wolf uses a shrinkage method to estimate the covariance matrix, And it also provides a confidence interval for each element of the matrix. Uncertainty method to explain in detail. Bootstrapping techniques can be used to assist uncertainty in the covariance matrix estimated using methods like empirical covariance. Challenges and fixes. Challenge 1. Explain in detail high dimensionality when the number of features is large compared to the number of data points. Covariance estimation becomes challenging. This can lead to unreliable estimates and potential numerical instability. Sample use case that resulted in Challenge 1. Imagine trying to estimate the covariance matrix for a dataset with 100 features and only 50 data points. This is a high-dimensional scenario, and traditional methods like empirical covariance might struggle to provide accurate estimates. Fixes to Challenge 1. Use regularized covariance estimation methods like graphical lasso or shrinking lasso that penalize large covariance values and promote sparsity in the estimated matrix. Employ dimensionality reduction techniques like PCA to reduce the number of features before estimating the covariance. Increase the size of the dataset if possible, as this will improve the stability and reliability of the estimates. Challenge 2. Explain in detail outliers. Outliers in the data can have a significant impact on covariance estimates, leading to biased results. Sample use case that resulted in Challenge 2. Consider a dataset with a few data points that are significantly different from the rest of the data. These outliers could disproportionately influence the estimated covariance, especially methods like empirical covariance that are sensitive to outliers. Fixes to Challenge 2. Use robust covariance estimation methods like Leduit-Wolf or Min-Cov-Det that are less sensitive to outliers. Pre-process the data to remove or downweight outliers using methods like outlier detection algorithms or robust scaling techniques. Consider using non-parametric methods that do not make strong assumptions about the data distribution, such as kernel-based methods.